Hello community, so great that you are back. Today we talk about how to generate videos with the latest AI, and we have a brand new AI architecture for you. And it is called GPDiT. Let's start here. Now, special service for you. Only today, May 13, 2025, I show you the best AI papers you have to read today. And then from those, I select the best one. And the best one is, of course, here, Generative Pre-trained Autoregressive Diffusion Transformer by Peking University and Tsinghua University. So let's start. Today you get an extra service and then we have a deep dive into the paper. What are the best paper of today? Today is Tuesday, May 13, 2025, and I've read more than 300 papers here, and I would like to show you the papers I'm interested in using outstanding papers of today. So here we have quantum state preparation via an LLM-driven evolution, and they propose here an automated framework for quantum circuit design by integrating LLMs into the evolutionary optimization to overcome the rigidity, the scalability limitation, and the expert dependence of traditional ones in variational quantum algorithm. They develop here now new ideas where 2-qubit quantum gate noises can be effectively mitigated via zero noise extrapolation from a spin chain system. And if you are into quantum systems, they have now an automated ansatz discovery. What a beautiful word. Ansatz, a German word. And they go here, starting from a generic physics agnostic template. They develop here a framework for feedback-driven loops. If you are here a little bit in using here DeepSeek Distill Q132b, yes, this is it. But you know, it's also very easy publications that I highly find interesting, an ecosystem here for adult learning. How can everybody learn with AI, through AI, AI helping here in the best possible way? We have a new research, this is here by the Georgia Institute of Technology, in architecture for AI augmented learning. Real interesting, here you have the archive link, and they examine here exactly how we can use AI for adult learning if you're not a student anymore, if you have continuous learning on the job about data architecture, personalization, scalability. And they are here from the National Institute of AI Adult Learning and Online Education. And we are developing an architecture for AI augmented learning to support adult learning through online education. Real interesting approach. But of course, if you want to go a little bit deeper into the understanding here of the AI architecture itself, there's a new model that I find highly interesting, and they tune here the reinforcement learning. They have a policy labeled preference learning methodology now. They called here policy labeled preference learning PPL. Remember, OpenAI had a PPO. Here we go now in the real last step here in the evolution here of reinforcement learning by human feedback. And they analyze how we can further optimize here our understanding. So I highly, of course, they have a policy optimization, a value model optimization. They work with a maximum entropy framework. I really like this study. This is called Policy Label Preference Learning. Is preference enough for reinforcement learning by human feedback? This is, I think, South Korea. Yes, Seoul National University, South Korea. And Korea University, Seoul, South Korea. Great. This is the archive link to you. This is already published May 6th, but it's out today. Let's move on. Yeah, learning. If you really want to go into learning, I would highly recommend this. This is a little bit about a more mathematical view on the internals of AI system. They have here a real deep dive, and you say, okay, what university could do this? No? And we are talking here a mixture of expert layers, and then we look here at the dynamic system, the evolution here of the mixture of expert architecture. And yes, if you want to have a deep dive, I highly recommend this. This is a study by MIT Mathematics and Harvard. So if you enjoy a little bit more abstract papers here, what about the power of fine-grained expert? Granularity boosts here the expressivity in MOEs. And they have a simple question: how do specific mixture of expert design choices influence here the model expressivity? And if you are into this, hey, I can guarantee you're gonna enjoy this paper. because especially later on, they have some really interesting ideas if you are interested into this. Let's talk here about planning. You remember how an AI plans here to provide a solution, to come up with a solution. Planning is one of the most important things. And of course, we combine this now with robotic systems. So we have here a brand new study. This is called Efficient Robotic Policy Learning via here a particular space backward planning. And this is done here by the researcher of Tsinghua University, Peking University, and Shanghai AI Labs here. Beautiful study. You have a GitHub repo available for you. And they tell you the current robotic planning methods rely on predicting multi-frame images with full pixel details, but they come up now here with, however, their forward planning schemes can still result in off-task prediction due to accumulation errors, leading to misalignment with the long-term goals. And they ask here a critical question: can robotic planning be both efficient and accurate enough for real-time control in the long horizon, in a multi-stage task? And they develop here a new methodology. If you are into robotics, there's a beautiful new idea of going backward here in your planning process. Next thing is, oh yeah, this is what I love, Internet of Agents. Finally, we don't have a single agent or a group of agents or only a cluster of agents or a multi-agent framework where we have MRLL, multi-agent reinforcement learning applied. But now we have the Internet of Agents, finally. So we have an agentic web. We have not AI agents or agentic AI agents. Now we have an agentic web. And the question is how to bring this together. And our AI agents have evolved from isolated now into autonomous interactive entities capable of receiving, reasoning, and acting without any human intervention. And in this survey, they introduce here the Internet of Agents as a foundational new framework that enables seamless interaction, dynamic discovery, collaborative orchestration among heterogeneous agents at scale. Highly interesting study. I just want to show you here one visualization that caught my eye here on, I like here, especially on the right-hand side, introduction, then the overview of Internet of Agents. What are the architecture? What are the key characteristics? Among here, then we have here the building blocks and the technology of the Internet of Agents. Given here, interaction structure, task orchestration, how is it done? Network topology structure, task allocation, task decomposition, the communication protocol from Anthropic MCP to Google A2A. Consensus and conflict resolution, economic models, trustworthy regulation. How does it work with blockchain and distributed ledgers? What about regulation, legal design, and the future research direction? I think if you are into, for example, cyber-physical secure Internet of Agents or any privacy-preserving agent interaction, this is a real nice survey. I highly recommend it. This is done, did I mention this here, by our colleagues in, here we are, School of Cyber Science and Engineering, Jiacheng University in Xi'an, China, and colleagues. Beautiful study. Here is your archive link, published here May 12th. So for me, this is almost today. Next study, what we have. Oh yeah, talking about AI agents and talking about the interrelation. What about agent reinforcement learning, the scaling laws? And there's now this idea of a spontaneous code execution for mathematical problem solving. This is done here by experts from Fudan University and, I can't even pronounce this, and colleagues. And they tell us, LLMs struggle with mathematical reasoning tasks requiring precise, verifiable computation. And while reinforcement learning from outcome-based rewards enhance the text-based reasoning, understanding how the agent autonomously learn to leverage external tools like a code execution remains crucial, and they examine this. And central contribution is we demonstrate that reinforcement learning processes key metrics scale predictably. And they observe some strong positive correlation. If you're into this, they have a GitHub repo for you. If you want to learn more about it, they identify 3 main causes. Really interesting. They have some mathematical benchmark. So if you're into agent reinforcement learning scaling laws and a more robust framework to leverage this for a spontaneous Python execution, I think quite some nice ideas here. Okay, next study is, let's go. Oh yeah, another survey, but real nice. What about you have a small LLM on your local computer infrastructure, on your, I don't know, laptop, PC, but you also want to connect to the real powerful model in the cloud? How is here the collaborative mechanism if you want to secure your privacy, your personal privacy? What about here the interconnect? What can we do? There's now a brand new service, May 12th. Those are the colleagues from Chinese Academy of Science in Chengdu and the University of Chinese Academy of Sciences in Beijing. And they examine exactly this interoperability, talking here about interaction mechanisms like pipelining, routing, auxiliary, distillation, fusion, about the key enabling technology and diverse application scenario driven by on-device needs, low latency, high privacy, high personalization, and an offline operation mode. Real nice if you want to learn more how they work together, what we have today implemented on protocols. Real nice study. Talking about what we have implemented here, I would like to show you a particular, I think it's a German work here by a team, and they talk about memory system architecture. And they say, hey, our agents are great now in reasoning, reinforcement learning, but they want to continuously learn. Therefore, we have to provide to our AI agents a new updated memory system, a better memory system architecture that we have to design for specific tasks of the AI. And they have here 3 stages: perception, ingestion, and recall. And you see sensor, camera, deliver here, I don't know, video. Then we have here capturing using here our vision language model and the embedding. Then we ingest it here with a representation in a graph with a vector store. And then we have the classical answer generation via an agentic RAG with LLMs. So how you build together here a new grounded memory system architecture for an agentic retrieval with the integration of graph, RAG. This is now a new system. Let me just check that I got it right. This is here, yes, Offenbach am Main, Germany. So the Honda Research Institute of Europe. Here we have the authors. Study is called A Grounded Memory System for Smart Personal Assistance. Great. Now attacking here, how can we optimize the memory system that it integrates here with the dynamic learning of the AI system itself, that we have here a perfect fusion. Published May 9th, and here you have the archive link for this particular study, and they talk here about the grounded perception, the new memory graph, and the agentic retrieval, how this all works together for an optimized memory structure. Yes, I would like to show you here another study that I personally find absolutely fascinating. You know, we are talking more and more about continuous pre-training. We understand that the pre-training of a model is so important. It is not enough just to have fine-tuning for a downstream task or reinforcement for the alignment of the LLM. But what about we do continuous pre-training? CPT now finally a deep dive into our understanding what happens if we have a continuous pre-training, not a fine-tuning, not a reinforcement learning. How does it have here an impact on the dynamic, on distribution shift? What does happen here to the loss function? How is now, for example, a continual learning, dynamics law, the hidden pre-training curve training here, distribution shift terms, and they have really a beautiful deep dive here. Also, the final transfer curve, what are the scaling laws here, and power law distribution shift. Real nice if you want to understand, hey, what is happening, what you have to watch out for pre-training here if you have certain thresholds. Great. Then, yeah, this I found interesting. Also, May 12, 2025. This is by, give me a second. This is here, Electronic Nanjing Technology University, Singapore, Hunan University, China, Shenzhen, China, University of Utrecht, Norway, University of Trento, Italy, London, UK, KTH Royal Institute of Technology, Sweden, Zhiying University, Korea, and Western Australia, and Singapore. Beautiful international consortium, Neural Brain, a neuroscience-inspired framework for embodied agents, for our robotic agents, for vision language action models. May 12th, here you have the archive link. Beautiful project page you have available for you. Embodied agent, neuroscience-inspired AI and they tell you what is happening here, especially if you want to implement today functions of the human brain. You want to imprint this here on different memory optimizations. But I think the most beautiful paper of today, May 12, 2025, here is your archive link. This is here by Peking University, Tsinghua University, StepFun China, and University of Science and Technology of China, and they go about generative pre-trained autoregressive diffusion transformer. So let's start now the deep dive into a generative pre-trained diffusion transformer model that is a new video generator and a much better video generator. You know why? Because you know what we are able to do? We have video few-shot learning enabled now. And you know what? It goes even more crazy because we will have a video in context learning. How does it look like? Imagine color. You have here some in-context example of a video sequence, and you know you have a black and white and you want to have it colored, or you have here black and white and exactly you want to have it colored, you have an input and you get the colored output. Or you have just some canny edges here for an image or a video and look input output, or you have style transfer in videos. Isn't this amazing? So how is this possible? Well, it all starts here with a diffusion transformer. Isn't this great? No, not a unit architecture, a diffusion transformer. And if you want to learn more about it, I have here diffusion transformer explained here in detail in new models and whatever. So you remember pure diffusion models here, and even our diffusion transformer applied to video often use here bidirectional attention over all the frames. And you know this system struggle here with a long-range temporal consistency and a strict causal ordering. It simply doesn't do it. On the other hand, we have our large language model, our autoregressive model, our transformer decoder structure, and they excel at causality and a sequence model. So how combine this? Because our LLMs, you know, we are still operate on tokens. Is there any way that we do not operate on pixels, raw pixels, but now on something else? Well, what a coincidence. Here we have GP. So what it stands for? This model learns like a foundational model, some broad understanding, but not only of text, but of visual concept, of object appearances in the video sequence, of motion patterns in the video, and of temporal relationship between the objects before being fine-tuned or used for a specific task. So this happens here in the pre-training. And this is why here the P for pre-training is so essential. And generative, yes, we will generate our videos here as foundational model, utilizing here a new form of a diffusion transformer. Because it is not diffusing now raw pixels or some quantized versions of raw pixels, but it is using now latent representation of video frames in a new mathematical space. If you have seen my last videos, you know that this is a continuation. Great. This new GPDiT takes now the powerful transformer-based diffusion model concepts and develops it further, because now he adapts for video generation by making it autoregressive at a frame level, and we operate here with our mathematical operations in a continuous latent frame. So this means we can even, if you want, optimize it further, because now the computational infrastructure that you need here for video operations is not that simple. So whatever we can do, make it simpler, make it faster, less memory. So we will have a new attention mechanism, a lightweight causal attention mechanism that is quite good, but less computational. And for the time conditioning, we will have a new parameter-free time conditioning, and I'm going to show you this in a minute. Now, you remember in the classical DITs here, we had, you remember this was the publication by UC Berkeley and New York University, we had our adaptive layer norm, 0 as an effective way to condition here the transformer blocks on the diffusion time steps. And yes, we had a video on this, and of course you remember here when I showed you here the DIT blocks with the other ln 0 integration. And cross-attention, we talked about this. Now, you remember also in my video about the diffusion unit architecture, I told you the models use a similar initialization strategy like here, because the use here is zero initializing here the final convolutional layer in each block prior to any residual connections. So you see, it is more or less all the same. If we are here in the DIT blocks, if we use here the diffusion net, or if we go now to the next step here with our GPDiT. Because in GPDiT, we use now a rotation-based time conditioning, and I will explain exactly why we have this beautiful simplification of a parameter-free rotation-based time conditioning. And it is just an alternative, but it is faster. It is an improvement to our Ada-ln0, and we have a better parameter efficiency. So if you want this rotation-based time conditioning, is just a way to inject time step information into the transformer block. I think this is the simplest information I can give you. So if you're interested, hey, let's open up the video. So great. So we have a generative, pre-trained, autoregressive diffusion transformer. And this is now a brand new novel framework for video generation. My goodness, we are now working with videos. Well, the aim is now to combine the strength of our autoregressive modeling, you remember this was great for temporal consistency, and our diffusion model, this was great for high-quality sample generation within a continuous latent space. So now, the main idea, if you want to remember one sentence, this is it. GPDiT autoregressively predicts future latent frames using here the diffusion laws, enabling here a natural modeling of the motion dynamics and of the semantic consistency across all the frames. You want to see the spark of genius that we had? Yes! As I told you, a new causal attention mechanism and a new time conditioning methodology is all we need. And yes, in my last video we were talking about artificial time, and what a coincidence that time is now so important in the dynamics now also of video generator. The core idea is simple, yeah? This rotation-based time conditioning, compared to Ada-ln0, is rather simple. And here you have the original paper, and if you want, yeah, this is beautiful, you can reinterpret here the forward process, diffusion process as a rotation in a two-dimensional space, and you see it's a simple rotation matrix, or, this is here my interpretation for really easy, a diffusion process gradually changes here how much of your original clean data, of your clean image data, and how much of a random noise are present in the noisy data. And just visualize this as a change in a point that rotates now in a two-dimensional space, where one axis of your two-dimensional space is now a pure clean data axis, and the other one is a pure noise. And the angle of the rotation of this point tells you the mixing proportion at any given time. You see, sometimes an explanation can be that simple. Here is now the overview of the complete GPDiT architecture of the inference. This is the framework. We just talked about this, and we just talked about and explained here the integration of the time step by a rotation operation. And we have the clean patches, the noisy pages, the Leon norm, the rotation, the new causal attention mechanism, simplified, faster, more efficient. Great. Now, I've already shown you here the publication by Peking University, Tsinghua University, StepFun China, and University of Science and Technology of China. And they have now this beautiful frame-wise autoregressive diffusion pre-training, also endows you the model with strong video understanding capabilities, not just generation. And I think this is here the real hidden power of this model, the video understanding capabilities that then lead to a better video generation. So again, the main 3 points: frame-wise, autoregressive diffusion in a continuous latent space, operates on a continuous latent representation. You remember we were talking about representation now for my last 4 videos. This is now a kind of an optimized video representation, likely from an autoencoder, a variational autoencoder, and the prediction is a denoising task. And this preserves here more intra-frame detail and allows the diffusion process to handle here complex pixel distribution directly in our space. So you have an idea. Our latent space is a high-dimensional space. The causal attention here, the simplified version here, is that we say, okay, we don't have to compute the complete complexity because We don't have this extra memory cost, but we go here with a pre-computing of key value projection once and reusing them without further inter-attention amongst themselves for each new frame is the way to go. And then we simply inject here the time dependencies here, and it replaces here the classical DIT ADA-LN 0 module. Rotation achieves here a similar effect of making the network's behavior time-dependent, but without any new learnable parameters for the time embedding itself. And this is great. It's not like in my last videos where we had to integrate an additional dimension, and this was our synthetic time dimension. So let's come to the results. Isn't it amazing? Video few-shot learning. I never thought I would show you here these simple ideas than this powerful implementation. Now, this pre-trained, remember, GPDiT exhibits here strong representational ability, enables here conditioning via sequence concatenation, allowing easy generalization if we use here fine-tuning over 500 iteration, batch size of 4, optimized here to generate transformation conditions on both the input images and the contextual demonstration. I would just like to show you some of the results. We have here our in-context example, our ICL learning, our fine-tuning, and then this is the input and this is the generated output. And as you can see, it works great because if we have here this sequence, it just works with input-output example for gray, for depth estimation, or for human detection. And I think this is especially interesting. Yeah? Look, here you have here a sequence of 2 people sitting here, and then you have the body skeleton here in a color encoded. Or here you have another situation as a few-shot example, in-context learning example. And here you have this. And automatically, if you give now this particular input, you see the model is able to generate this particular output. Or you have here these children running here around in the scene. You see this is the interpretation. Few-shot learning, in-context learning, or fine-tuning here on few-shot example. What an amazing ability that this system is able to perform this just with some very, very few examples given here for this video generator. If you're interested in this kind of video, if you maybe are interested to learn more about the next methodology, hey, why not subscribe, and I see you in my next video.